Alright, let's take a look at a symmetric alkyne. We're no longer talking about terminal alkynes. So we're looking at a triple bond that has exactly the same things attached to each end. When we treat this with Hg2 plus and H3O plus, the H plus could actually add to here and the plus here, like I've shown, or we could be looking at the H joining here and the plus joining here, which would be the opposite of what we've got here. However, what's going to happen is, in the end, we're going to end up getting the same product. There's no difference in stability, of course, between the positive being here and the positive being here, because they're attached to exactly the same number of carbon atoms. So the fact that we've got both of the same things attached to the triple bond is going to lead us to just one product if we start off with a symmetric alkyne. If we use an asymmetric alkyne, that is something where we've got two different things attached to C triple bond C, then what we're going to do is end up with two different products. Now what's going to happen is, in the first step, the triple bond will react with the H plus, and we will end up getting the O joining on to this C plus, which will eventually come down and have us create this ketone with the C double bond O next to the cyclopentyl group. If we take the other option of joining the H plus to the triple bond, the H will end up here, the plus will end up over here, and all the way through the water will add to this C plus, and we end up with the C double bond O next to the cyclobutyl group. The mechanism here is exactly the same as it was when we first looked at the terminal alkynes. The other thing to note, of course, is that even though this is asymmetric, the stability of the C pluses that we're getting here, no matter which way we add the H plus, the C pluses will have pretty much equal stability because they have the same number of carbons attached to the C plus. So we actually have pretty much a 50-50 chance of getting either ketone in this instance. Alright, I will go through and show just one of these so that you can assure yourselves that the mechanism is the same as what we dealt with the terminal alkynes. We'll start off with the same one as I've got in the diagram. So the two products we'll end up with will be this one. And I want you to take note of the fact that the bond geometry is changing because we're changing from a triple, in this case, to a single bond. So we can have the C double bond O there, or the C double bond O can end up on this one. Alright, so there we go, there's our line structures. So looking at the mechanism, and what I'm going to do is choose to put the plus on this carbon, which leaves the hydrogen over on this carbon here. We'll have the water come in, attack the plus. Again, notice the bond geometry I'm using here, showing 120-degree bond angles about the double bond. In the next step, the H plus is lost. The arrow comes from the H O bond and goes to the oxygen. And the reason for that is because we've got two electrons in this bond. One belongs to the H, one belongs to the O. If we have both electrons go onto the O will end up having its positive charge neutralized, and we'll end up getting a neutral compound there with the loss of H plus. Right, this produces our enol, and the enol can then be converted into the keto form, and I'll do this one in one step, just like I showed you in the terminal case. You could do it in one step if you wanted to. And on the test I don't mind if you do that. And then we'll have H plus left over. Alright, so that would be the mechanism right there again. Remember, the mercury is catalytic in this reaction and probably helps to get this H plus addition to occur to the triple bond in the first step.